Welcome to everyone watching this ISAH McCulloch and Till Award interview. My name is Maria Jasinskaya, and with me I have Marcel Rommel, and we are both representing the ISAH New Investigator Committee, and we will be conducting this interview with this year's award recipient, Dr. Eirini Papapetrou. Dr. Eirini Papapetrou is based at Mount Sinai Hospital in New York City, and she is being recognized with this award for her innovative and high-impact achievements in leveraging induced pluripotent stem cells to model and study the mechanisms of myelodysplastic syndrome and acute myeloid leukemia, which I'm sure she will tell us more about in just a moment. So, Eirini, thanks for joining us today and congratulations. I will now give the word over to Marcel for our first question.
Yeah, congratulations again for receiving the award. And I think we can start with the first question is, what brought you into the field of hematology? What did you find fascinating about it?
Yeah, well, thank you very much. So what brought me first to hematology was when I was in medical school and starting to study internal medicine and learning about mechanisms of disease, it became kind of obvious that hematology was the part of medicine that was really much closer to molecular mechanisms of disease. We had, compared to what we knew about other areas of medicine, in hematology, we had a very good handle of how diseases are develop. We had a much better understanding of the mechanisms, the genetic mechanisms, the molecular mechanisms. And I think that was intellectually much more satisfying and kind of made me very interested in this area. And I think, of course, the reason for this is quite obvious. The main reason is that, hematology has always been has always had this advantage where we have easy access to patient cells. And so even before we had very elaborate technologies, a lot of firsts in biology and in medicine happened in this field. And I think that was kind of my entry point as a training medical doctor. That was my first exposure and my first sort of spark of interest in this area.
I can definitely relate to that. It's really fascinating that we have such a long history of blood since, we know that it exists. So, how would you describe your science you do with the new technology you established for the scientific community? So what is really, where did you go? Where did you get your inspiration, curiosity, knowing what is in the MD field? What do we need?
Yeah, well, first, the way I think perhaps and related to the previous question, perhaps the first sort of seeds of this were planted long ago when I was still between clinical practice and doing a PhD, and I first sort of became exposed to the tools that we have to study disease and particularly hematology. And on one hand, we had patient cells that we could get from the blood and bone marrow, and we could study them. But there was very limited things we could do, especially back then. But even to this day, there's still limited material, and we can't culture them, we can't manipulate them much. We don't have controls, we don't have repeats. On the other hand, we had cell lines and we had other models that we could do much more elaborate experiments, and we could have controls and repeats and statistics. And but then we would always be left wondering if this, what was the relevance of this to the real deal. And so many years later, when I was in at Sloan Kettering as a postdoc, and that's when iPS technology was first announced by, as Shinya Yamanaka, made this fascinating discovery, and everybody was so intrigued, and including myself. And in the first months and years, we just all started trying to see, to learn, how it works. Does it work? And of course, it became obvious that that's a tool with which we can model human disease. And the first diseases to be modeled were, the genetic diseases, classic genetic monogenic diseases, because what IPS technology offers is a platform to make really precise and faithful genetic models of human disease. So germline disease, germline mutations, like thalassemia, and also in other fields, all sorts of diseases. But when I was starting my lab, I thought that why not use this to also study diseases that are caused by somatic mutations, and of course the most common of these class of diseases are malignant diseases. And so with this premise, I decided to see if that platform, that technology, could be developed as a model to study blood cancers and pre-malignant conditions. And that's kind of how it all started. And over the years, we back then there were so many unknowns that we had. We didn't know if malignant cells could reprogram. We didn't know. We didn't have very good protocols to differentiate the cells to hematopoietic cells, and all these were defined. We didn't have. That was actually even before CRISPR, so we didn't have great efficient tools to genetically engineer those cells. So we didn't know a lot about the mutational landscape of blood cancers yet. Our knowledge of this was very incomplete, but so all these over the years came in and refined things, and that's kind of how we developed this over the years, of the past almost now 15 years.
I think you nicely described the challenges to overcome right now, because that was one question. But had you had at any time point, for example, an accidental moment where you thought, okay, something never you anticipated or hypothesized, and has this changed your way doing research or the direction of your research? Has this ever happened?
Well, I mean, the first was actually the Yamanaka experiment, right? That was, I think, a very defining event that changed completely the direction of my research. When I was a trainee, I was then studying genetic engineering of hematopoietic stem cells, and suddenly, we had this whole other new kind of approach. Other times, of course, there have been many little moments where something happens that makes you rethink completely things. One time I can think of was when we had started reprogramming cells from patients with leukemia, and we realized that indeed, because reprogramming can be done in strictly clonal conditions, and so we can isolate single cells. So at that time, we realized that you can really isolate different clones and subclones and reconstruct the clonal composition of a sample. I think that was a realization that really opened a lot of new ideas about what we can do. Other moments where things when, a lot of the time when you have data that don't quite fit, and you're trying to make sense of it, and then there were times when, for example, when we were studying venetoclax resistance in and venetoclax responses for the study that we published last year. At first, things were not making sense so much because we were seeing those different responses in the leukemia stem cells to this drug, venetoclax, and we were baffled by that until we realized that sort of tracks with RAS mutations, and therefore it's the RAS mutational status that defines the resistance or sensitivity. Another example is more recently, we have a study where we were trying to understand the role of interferon signaling in HSCs, and particularly those with chronic hematopoiesis mutations. We had data that were very, confusing, and also a lot of the literature is very confusing. And then at some point, we did some experiments where that kind of clicked a little bit in place, and now we have a better idea of how this works. And this is a much more complex mechanism than we thought initially. So yeah, many little moments like this over the years have come.
So scientific funding is notoriously conservative. And what was the biggest, on this topic, what was the biggest professional risk that you took? For example, a project that everyone told you wouldn't work or was not feasible or dead, that eventually led to an interesting discovery.
Well, I think it was mainly, again, when we're studying the lab, and this whole premise that using iPSCs to model diseases that are not, the classic genetic monogenic disorders, but more complex diseases such as cancer. I think at the time it was a very new idea, and understandably to some extent, there was a lot of skepticism. There were a lot of unknowns, and so I think at the time that was viewed as a quite radical proposition. On one hand, it was innovative, but on the other hand, people would raise a lot of concerns about, the feasibility and a lot of things. So that took a little while to get, but fortunately, we were able to get funding and support and do it. And then over the years, that became easier.
Would you do it again? Now knowing the whole journey, would you establish it again?
Absolutely, of course. Of course. I mean, now, especially now knowing that no, I would totally do it again. I was always convinced that I think, I did it because yes, there were a lot of unknowns, but I always thought that the premise is solid, right? That the rationale is solid, and most of the problems were technical, not really conceptual. And so with that, I thought that that some problems will be solved and others that can be bypassed, and maybe, as we go, we'll learn something. And I think that was indeed that was what happened.
Yeah, I think you nicely said with the newer technologies which come up every year now, it improves the field more and more and very quickly. So I think it's a great time to have this technology and to even improve it further. I really like that. So speaking from about the ISCH perspective, what did ISCH for you over the last years, decades when you've been a member? So what did you enjoy the most from ISCH? Also from the perspective as a MD versus the scientists in our community, how do you see that? And what do you think should society do to foster what we have, this really beautiful scientific community with exchange? So what's your opinion on that?
Yeah, I think what's one of the best things about ACH is really the community, and you know, how it brings together the people from all over the world in the annual meeting, but also in all these other, you know, events throughout the year, and how it sort of supports and bridges the basic research in hematology and experimental hematology with more, you know, disease, you know, oriented research, more translational questions, and how I think it is a great home and a great venue for trainees to interact with each other, to interact with established investigators, the leaders in the field, learn from them, get mentored from them, even in informal ways during the meeting, get feedback. I mean, I think a kind of special part of this is also the international aspect of this, and how, you know, the meeting moves around the world every year. I think this is a great also opportunity to be exposed to other cultures and to other investigators from, you know, all over the place. I think now science and research is becoming more and more decentralized. There's lots of innovation and resources that come from all places in the world. I think that's a great opportunity. And, you know, as you may know, in the past few years, we've also had partnered with ISCH annual meeting to host a symposium, a pre-meeting symposium the day before the main meeting starts on human pluripotent stem cell-derived hematopoiesis. And this has been, I think, critical in building also this kind of more young and emerging community, and providing, again, a home for people to come and learn about the more recent advances, find new mentors, learn, you know, interact with each other, get new ideas, maybe solve problems that they have. And I think this is, you know, really important to train, you know, the workforce of the future in newer technologies, but also kind of, you know, bring everybody together.
The last question is, what advice would you give any young scientist in the field of hematology, if you could give them one, if they want to pursue a career, regardless if it's academic or somewhere else in hematology? What would it be?
So I guess the advice I would give would be to find what you really enjoy doing and what you're good at doing, and become really, really good at it and stick with it. And I think if you do this, I think most likely this will lead to a fulfilling and happy life, and a lot of other things will fall into place. It seems simple, but I think that's kind of the essence of doing science, really, and that's my advice.
Thank you so much for
Keep
that
it simple.
Thank you so much. That is really good advice. So that was our last question. So thank you again, Eirini, for joining us today, and huge congratulations again on the award. And we really look forward to seeing you and hearing your talk in Frankfurt later this year. Thank you.
Thank you so much. Thank you. It was great talking to you, and thank you so much, and thank you for this award. That is an incredible honor. Thank you.